Hey, 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 it's Dr. J. Today we enter a whole new world of calculus, the derivative, probably one of the most important features or definitions, aspects of this course. And so there are lots of different interpretations of the derivative. So let's start with just something we've already discussed. So if you have a function, so f of x, or we could write it out y equals f of x, or simply f. The derivative of f at x equals a is the slope of the tangent line at the point a f of a. So we've already done several examples, and we'll see some more today, but with the graphing and the slope of the tangent line. So this is one definition of the derivative of a function at a value or at a point, the slope of the tangent line. This is equivalent to the instantaneous rate of change also known as AKA instantaneous velocity. When we're talking about money, we don't use the term velocity. We don't say that the money or the change in dollars has a velocity, or when we're talking about how fast something is going up or going down, we think of it as an instantaneous rate of change when it's an abstract concept. But if it's an object in space like a ball or a rock, we would refer to it as velocity. But the formulas and the concept behind how we calculated them are identical. And it is defined in several different ways. The first definition is the limit as x approaches a of f of x minus f of a over x minus a. So this can be thought of as the limit of the slope, right? So this is the slope formula, the average rate of change formula between two values, x and a. Yeah, x is equal to a is the value in which we are approaching. So x is getting closer and closer to this value, a. So we'll call that definition one, I guess. We'll call that our first definition of the derivative. I've used up all my board on this first definition, which is probably okay because I'm not going to give you the second definition until we do a few examples of the first definition. Okay. All right, so we've seen a lot of functions in this course, and one of the most common ones would be the quadratic function. So find the limit x approaches a Oh, I got to give you a function first. Let's do 8x squared minus 2x plus 3. And then let's find the limit in this definition here. F of x minus f of a over x minus a. So in other words, I'm just going to put in the cloud here, the derivative of f at x equals a by definition 1. So we're using this first definition to find the limit as x approaches a for this particular function. All right, let's get right into it then. So this will be I'm going to give myself lots of room. The limit as x approaches a. Here's my function. So I've got 8x squared minus 2x plus 3 minus 8a squared minus 2a plus 3. So this is f of x, this is f of a, all over x minus a. That's equal to the limit as x approaches a, 8x squared minus 2x plus 3 minus 8a squared plus 2a minus 3. Right? We've done this before. When you distribute the negative, changes the signs here. So this 8 becomes negative 8, positive 2, and negative 3. You also get a little bit of canceling. Negative 3 and positive 3. We're going to do what's called grouping here. So we're going to do 8x squared minus 8a squared. So we're going to group together our square terms. We're also going to group together our linear terms. The constant terms have canceled. Now this is where all the magic happens. You're going to leave yourself some room for this last line. I could probably squeeze it down here. Let's see if I can squeeze it down here. So you're going to factor this. Now this is going to be 8x minus a, x plus a. All right, this is calculus. So, review your algebra. I've been going over it for the last several weeks. And in the interest of time, I'm going to take a leap of faith. Just assume that everybody remembers their basic factoring. You pull out the 8, and then you have two perfect squares, x squared and a squared, and then you know that special recipe, x minus a, x plus a. Okay. And then watch what I do here. The denominator, I'm going to go ahead and put parentheses around it just so that it kind of matches. And I'm going to write it twice. You've seen me do this before. I'm going to do that a lot today. The denominator, I'm going to write it twice. And then in the second factor, I'm pulling out a negative 2. All right, be very careful with negatives. When you factor out a negative 2, this second term here, the 2 and the negative come out, and that changes the sign. And the whole reason why we do this is because our goal is to cancel the denominator so that we don't have division by 0. So this is now the limit as x approaches a of 8x plus a minus 2. And the denominator is now a 1, which I generally won't write the 1. I'm writing it in this example because it's example 1. Generally, I will just write the numerator. Okay. Well, that's it. That's the answer. That's your limit. You do have to take the limit, but I mean, this is the algebraic work that gets us to the step where we can finally do the calculus. All right. So the last step is calculus. Now that you've canceled the denominator, there's no more division by 0. Because notice, had you tried to take the limit at the beginning of the problem, you would get division by 0, and it would be an indeterminate or unresolved form. Right. Now we can plug in A. Plug in A. X equals A. Right, so the X becomes A. So that's going to be 16A minus 2, and that is our final answer. Right? A plus A is 2A, and then times 8 is 60. The minus 2 is the constant term, so just leave it off to the side here. Don't combine it with the rest of the terms like basic algebra principles tell us. So that's the answer. By definition 1, the derivative of this function at x equals a is 16a minus 2. Okay. Now, a is a number, right? You got to keep that in mind. X is the variable, but A is the number that we are evaluating this at. So if you had a number for A, then this would actually give you a slope. Right now, it's sort of a slope in waiting, right? It's waiting for an A. You tell me who the A is, and then I can tell you what the slope is. So let's do another example where the A is defined. So let's do x squared plus 8x minus 7. And let's do the derivative at 4. So this is the derivative. Again, I like to have this little cloud here, so that when I'm talking about what this means, it's a limit, it's a function, right? Those are all things that we've dealt with in this course. But now we have this definition. This is the derivative. Let's say deriv of f at x equals 4, right? Because there's your a. So now you have a choice, all right? It's your choice. You can plug in A now, plug in for now, or wait, use A, then replace with 4 at the end. It's your choice. Now, I don't know if you know which you would like to do, right? I mean, I'm giving you a choice between two options of which you may not know, what those two options are like. So how do you choose between two things when you've never had either one of those things? Well, you've kind of seen one of them already. You've seen what it's like to wait, right? Let me show you it one more time. All right, so let's do option 2. We'll call this the weight option. Option 2. So what you would do is you'd say the limit as x goes to a of x squared plus 8x minus 7 minus a squared plus 8a minus 7 over x minus a. And you would do what we just did. All right, so let's do it again. This time, we're getting a little better at it each time. So you're going to get x squared minus a squared plus 8x minus 8a. The 7s are going to cancel. You're going to get the factoring. X minus a, x plus a, over x minus a, 8 over x minus a. The same exact steps we just did. I mean, the numbers are slightly different, but... And then you would cancel. X minus a, x minus a, x minus a, x minus a. And you get the limit as x approaches a of x plus a plus 8. Yeah. That's all that's left here. X plus a plus 8. Everything else is canceled out. So then you would do the limit. So remember, the limit is just replacing x with a. So you're going to get 2a plus 8. And then the function says, or the derivative is the derivative of the function at 4. So a is 4. So 2 times 4 plus 8 is 8 plus 8, which is 16. Okay. And so the answer would be 16. Answer 16. Right. And what does that mean? Well, with the original introduction, I said this is the slope of the tangent line at x equals 4. This tells you the rate of change at x equals 4. Or if it was an object, it'd be the velocity of that object flying through the air or something. Again, the velocity would require some situation in which we're measuring, how fast it's moving. Generally speaking, we just give it a number. We say it's 16. 16 to 1, if you want to think about it as a ratio. So for every 1 unit, it's going up 16 units. For every 1 unit that it goes over. So there's all these, mental interpretations of what the derivative is actually telling you. So that's option 2. The reason why I showed you option 2 first was because I'd already shown you how to do it with the replacement value a, right? The nice thing about option 2 is that we've done it before, and if you want to try another example of this, you don't have to do the whole problem again. If you want the tangent line at x equals 6, well, you just take this answer here. This is sort of your in waiting. This is your answer in waiting. And if I change this to a 6, well, then you don't have to do the whole problem again. You just put a 6 in here. If I change it to a -3, you could just take this result and put -3 in there. So this is a little bit more flexible because it's in waiting. Now, maybe you don't want to wait, right? Maybe you just want to get to that 16 quicker. So option 1, I did option 2 first, straight to the point. And literally, we mean straight to this point right there when x is equal to 4. So that would be the limit as x approaches 4 of x squared plus 8x minus 7 minus 4 squared plus 8 times 4 minus 7 over x minus 4. So you would not put an a in here. You would put the straight to the point number here, 4. Now we already know the answer is going to be 16. Let's see. If we don't get 16, then we know something's wrong. So you're going to get x squared plus 8x minus 7 minus, what do we got here? 16 minus 32 plus 7. Double negative there. All over x minus 4. 7s are going to cancel. The limit as x approaches 4 of x squared plus 8x minus, what's that, 48 over x minus 4. Negative 16, negative 32 is negative 48. So that's the limit as x approaches 4 of x minus 4, x minus 12 over x minus 4. Actually, x plus 12. Got to be careful with the signs. It's a negative 48. So that would be a negative 4 and a positive 12. I usually guess the numbers first. The first thing that popped in my head when I saw 48 was 4 times 12. And then I think carefully about the signs. The 4 has to be negative because these must cancel. Right? If you don't get a canceling in this very last step, then something is wrong. All right, and so then this is the limit of x plus 12 as x goes to 4, which is 4 plus 12, which is 16. Check. It's exactly what we got last time. So you can wait and plug it in at the very end, or you can get straight to the point, plug in the number, and get your answer. So those are the two options for the derivative of a function at a particular value or at a particular point. Well, you know, this is math, and we always like to have multiple definitions or multiple versions of the same concept, right? It's not that we're trying to overly complicate it. It's a hard pill to swallow, but we're actually trying to make things simpler by giving you more options, right? So in other words, I think of them more like roads, right? So this is one pathway, one road to get to the answer. But I'd like to consider another option. Definition 2 of the derivative. The derivative of f at x equals a. Definition 2. Instead of going towards a, instead of the limit approaching a, we can use the concept of the secant line. Remember, the secant line was f of a plus h minus f of a over h. This is also known as the difference quotient or the slope of the secant line. I haven't used that term yet in this course. I know that I've used it in my algebra courses. So if we have any repeat students here, this is what we call the difference quotient, also known as AKA the slope of the secant line. And I know that we've definitely done that. Yeah. And so what we do is we take the limit of the slope of the secant line, and that is another interpretation of what the derivative is. That is our second definition of the derivative. In this particular assignment, I will teach you both definitions, and then I will ask you which one I want you to exhibit. I'll say, use this definition or use the other definition. So I want to make sure you understand both definitions. Once we get beyond this, once we get deeper into the subject, it will be up to you. So you'll just have a problem, and the problem will say, find the derivative, and then you will be equipped with these two definitions, and you can say, well, for this particular problem, I prefer definition 1, or for this particular problem, I prefer definition 2. All right? There might even be a third definition coming down the road. Okay, there's no limit to the number of definitions, pun intended. So example 3, so if f of x is x squared minus 7x plus 9, find the limit as h goes to 0 of this, f of a plus h minus f of a all over h. That's taking up a lot of space. Probably going to have to evict some of this writing in a minute. Okay. So again, I really like to emphasize what this is. This is the derivative of f at a. Okay. Well, let's do it. So this is the limit as h goes to 0 of a plus h squared minus 7a plus h plus 9 minus a squared minus 7a plus 9 all over h. That's the limit as h goes to 0. We've seen this before. A squared plus 2ah plus h squared. I'm picking up from down here, bringing it up here. Sorry if my board was longer, my camera range was bigger. I could just keep working down. I can't though, I'm out of space. 7a minus 7h plus 9 minus a squared plus 7a minus 9. So this negative changes those signs. If you're having this feeling of deja vu, oh, I feel like we've done this before, it's because we have. We've spent several weeks talking about limits. We've talked about slopes, talked about secant lines. We've drawn graphs. We've used tables. And now we're just taking all of that and, naming it. That's all. We're just putting a name on something that we've already been doing. We're calling this the derivative. So this is the limit as h goes to 0. Oh, this is my favorite part. One of my favorite parts. I mean, I have lots of favorite parts, but I like to cancel. It's because that satisfying kind of, you're simplifying the result. When some people think that it's getting more complicated, I say, hold the phone. It's actually getting easier as we go along. One of the benefits of your investment in this course is that you're going to get paid back with simplicity. 2a plus h minus 7. That's the reward. There it is. It all paid off. And remember, I've said this before, calculus is 90% algebra, so 90% of the work you do is algebraic, and then one tiny little, bit of calculus. So I don't even know if you can call that 10%. It's even less than that. It's just one step. H goes to 0, so you're just plugging in 0 here. 2a minus 7. There you go. So this is the derivative of f of x at a. Okay. And now it would be, if the question was just asking for that, then I'd be done. If the question was asking for a particular number, then I could plug in that number. So I could say, example 4, watch how easy this is. Let's make a be -2. I'm not really going to do the whole problem again, right? I'm just, for the sake of numbering, I'm going to call it example 4. So now I've got everywhere that there's an a, I'm putting a -2. So I want to know, what's the derivative of this function at -2? Well, I already know. It's going to be equal to 2 times -2 minus 7. Just plug in the -2. And the answer would be -11. Now, I could bore you with another 10-minute, exercise. We could take this equation, write it all out, work out all the things, do all the canceling, plug in the numbers, and then I would get -11. You see? But we don't have to do that because we've already experienced it once. All right. So that's the idea behind the limit, behind the derivative as a limit. And so that really brings us to an interesting point here. There's a lot of, confusion between what's the X and what's the A and what's the H and in the F and the Y. We have all these different characters and symbols that we use. And does it really matter? It's a good sort of philosophical question. Does it really matter what symbol we use? It doesn't have an easy yes or no answer. I mean, the answer is sometimes it does matter because, if you use the wrong symbol in the wrong place, it can cause the result to be incorrect. So in that case, the answer would be yes, it matters. But there are other cases where I could use a different symbol and I could still get the same result, in which case you could say that it doesn't matter because you could change it. So whether or not something matters in mathematics can be answered by you if you have that curiosity. Ask yourself, what if I did it differently? Would I get the same result? And if the answer is yes, you get the same result, well, then the answer to your inquiry is no, it really doesn't matter. You could do it differently and get the same result. You're probably listening to me say this and you're going, well, isn't that just true with everything? Isn't everything like that? If I change something but the result is the same, then that means what I did by altering the symbol didn't really matter. I don't know. I don't want to get too deep into the philosophy, but I am going to get deep into the mathematics. Let's just not use any different symbol. Let's just use f. The derivative is a function of x. The derivative itself is just another function of x. So let me show you an example. All right, so here's a function of x. Find the derivative in terms of x. In other words, do not specify any value. I'm not going to specify any specific value. Not, no, I don't know which, I like no better. So there is no, or there is not a specific value of x. I could just think of this as a function. So the limit as h approaches 0 of f of x plus h minus f of x all over h. And so I'm not going to put a specific number in for a. I'm not going to use 4 or 2 or 6 or any specific number. All right, let's do it. What are we waiting for? Limit as h goes to 0, 6x plus h squared plus 7x plus h plus 9 minus 6x squared plus 7x plus 9 all over h. Six x squared plus 2xh plus h squared plus 7x plus 7h. I feel like we've done this before. Distribute the negative. All over h. Running out of space. The limit as h goes to 0, 6x squared plus 12xh plus 6h squared plus 7x plus 7h plus 9. Squeeze this in. Minus 6x squared minus 7x minus 9 all over h. Comes my favorite part. The 9's will cancel, the 7x's will cancel, and the negative 6x squared and the positive 6x squared will cancel. So this is the limit as h goes to 0 of 12xh plus 6h squared plus 7h, all individually over h. Which is the limit as h goes to 0 of 12x plus 6h plus 7. So I haven't actually plugged in an a, right? This is a function of x and h. The limit now is going to apply only to this one term. That's going to become 0. 6 times 0 is just 0. And this is the derivative as a function of x. And you might be looking at this going, wait a minute, isn't that exactly what you just did in the last example? Yes, it is exactly what I just did in the last example, except for I called it a last time, and now I'm calling it x. So let's go back to our philosophical inquiry. Does it matter whether you call it a or whether you call it x? No, it doesn't matter. A function of a function of x. We might even do a function of t if we're talking about time. We could use lots of different symbols, but the concept is that this represents a thing called a function. Well, when we invent things, we like to give them names. So this is definition 3. The derivative as a function it's exactly what we just did in this example. And this is called a prime. So we read this as f prime. This symbol here. It's an apostrophe. We call that f prime. So this is the definition of the derivative as a function of x. As a function of x. So we say the derivative as a function of x is f prime of x. And so my answer is 12x plus 7. So in example, what were we calling that? 5? F of x was, oh God, what was f of x? I can't remember. It was 6x squared. Yeah, 6x squared plus 7x plus 9. Yeah, that was it. And then f prime of x, I'm just summarizing the example that I just did. I'm not changing anything, trying not to. So this is f prime. I never know whether to curve my primes. Some people just make it like a dash. Try not to make it look like the number 1, though. I mean, there is going to be a time where we do put a number 1 up here, and it will be a different thing. So we try not to make it look like a 1. We try to give it a little bit of a flair, you know, a apostrophe symbol or something like that. So that's f prime. So that's your answer to example 5. Using this new definition, definition 3. Well, it's time to start looking at the graphs now, because now that we have these functions and we've gone through 3 different, definitions of the same object, right? We're just defining it in 3 different ways. And we're now going to be able to interpret the results geometrically by looking at the graphs. So let's do example 6. I'm going to need a lot of space for example 6. So say goodbye to number 5. Bye, number 5. Start way up here. So let's start with a function, x squared minus 3x plus 2. And let's think about the derivative So let's find the derivative, f prime of x, and then complete the table. Where should I put my table? I'll put my table over here because we won't need it for a while. So this is a lot like the tables we've done in the past, but now we're labeling it as a derivative table. So it's not a function table. This is a derivative table. So after we have the derivative, we're going to complete this table. I'm just going to pick 5 very simple numbers. I sometimes refer to this as a spread. Yeah, -2, -1. So you got 2 negatives, 0, and then 2 positives. You can do a larger spread if asked, but this is usually sufficient. And when I break out my graphing plane, it'll be easy to visualize what this looks like. Before we can complete the table, we need to find the derivative. So f prime of x is the limit as h goes to 0 of x plus h squared minus 3x plus h plus 2 minus x squared minus 3x plus 2 all over h. All right, that's the definition. You might be tempted not to write the word limit as many times as I am. You know, in your notes, you could just say lim, or some folks will just do like a cursive L or something to remind them that they're taking a limit. I would recommend writing something, because if you don't write it, you'll do all the algebra and then you go, oh, shoot, now what, right? So writing something to remind you that you are still in a calculus class is not a bad idea. In fact, it's a very good idea. But I will leave it to you in your notes that you're writing at home to use any notation that will help you stay on track. 90% of the work is all going to be right here anyway. I know that I'm being recorded, so I want to be pure to the subject here. So you're going to cancel the 2 and the negative 2, the 3x and the negative 3x, the x squared and the negative x squared. All right, don't cancel the h yet. Hold off. If you try to cancel the h right now, it typically will not go well for you. I've seen that, and it ends badly. Wait till this last step. Write the h 3 times or 2 times or however many times matches the number of terms that you have left. So you have the limit as h goes to 0, 2x plus h minus 3, which is 2x minus 3. So this is your f prime. All right, f prime of x is 2x minus 3. So this is what I'm going to use to fill out this table now. These numbers are relatively simple, so I think we can do them with mental math, but maybe I'll do a little scratch work right here. So let's do negative 2. So 2 times negative 2 minus 3, that'll be negative 7. Let's do 1. Negative 1. 2 times negative 1 minus 3. That's negative 2 minus 3. That's negative 5. 0. Oh, I can see that. Negative 3. I don't even need to write that one down. Right? 2 times 0 and then minus 3 is just going to be minus 3. Or how about 1? 2 times 1 minus 3. That's going to be negative 1. You'll start to notice a distinct pattern here. And then 2 times 2 minus 3 is going to be positive 1. So the table is a derivative table. Right? It's a table of the derivative. The graphing board says I'm back. All right, welcome back. Let's see. So 1, 2, 3, 4, 5, 6, -7. I'm kind of looking at my y values here. 1, 2, 2, -2. I'm not going to label every point. Let's see, 1. So I've got -2, -7 right here. -1, -5. I'm off by 1. So there's -7, there's -5, and then 0, -3, and then 1, -1, 1, -1, and then 2, 1. So these dots are the derivative 2x minus 3. In the future, I'll probably just connect them with a straight line. But for this example, I just wanted to show you the dots. Once you have determined that the shape is, a line, then you can connect them with a straight line. It's not always going to be a straight line. All right, I just want to make that clear. In this particular example, it's a straight line. It depends on the result of the derivative. If the derivative is a linear function, then it will make a straight line. Next, we want to dive into what are all the different possibilities for the shape of the derivative. Now, we won't be able to do all the possibilities, but we can certainly do some of the more common ones that occur at this level of calculus. All right, so that's the end of that one. So you've kind of seen the rule of 3 here. I hope, before I erase it, take a look at what you have. You have the numeric, that's the table. You have the geometric, that's the dots or the line. And then you have the algebraic, which is the function itself. And all 3 of these things all work together, and that's what we call the rule of 3. And if you're ever missing one of the 3, well, hopefully you have at least one of the 3. If you're missing all of them, it's very difficult to do any math, right? But if you have one of these 3 things, you can always determine the other 2. Typically, unless there's some obstacle in your way preventing you. But when things are going well and you have all the relevant information, then all 3 of these things should work together harmoniously and holistically. Okay, so in our next couple examples, I really wish I had a second graphic board. In the next few examples, the grid itself is a little bit too large, takes up too much space, so I'm just going to do freehand graphing. The next few examples. So suppose you're given the graph of a function find the graph of the derivative. Okay. So these are just going to be freehand, so we don't have to be very specific. Well, we have to be relatively specific, but we don't have to be perfect. So suppose this is 4, and this is negative 2. All right, and so this is your function, f. Okay, so what's now the graph of the derivative? Call that f prime. Well, remember, the derivative is the slope of the tangent line, but this is a linear graph. The slope is 4 over 2, which is 2. Now you got to be careful. This is a negative 2, but the slope, I feel silly doing this, but I'm going to go ahead and do it anyway. It may have been a while since you did basic algebra, so I want to show you why this negative doesn't come out to be negative in the final answer. As soon as you see it, you're going to go, you didn't have to do that, Dr. Jordan, but thank you anyway. Remember the formula for slope? It would be 4 minus 0 over 0 minus negative 2, which would be 4 over 2, which would be positive 2. So the slope, the derivative, is just a horizontal line at 2. So if this is the function, then this is its derivative. Let's call that, I guess, part A. I want to do another one of these. I want to do another one. How about part B? What else? Let's just call it part B. So suppose this is negative 3 and this is negative 1. And this is my f. So again, negative 3 is actually 0, negative 3. And then negative 1 is negative 1, 0. So the slope is negative 3 minus 0 over 0 minus negative 1, which is negative 3 over 1, which is negative 3. So the derivative is the slope. So when I graph the derivative, I would graph a horizontal line passing through negative 3. This is what the derivative would look like. So what I'm trying to do in these examples is establish, using one of the 3 aspects from the rule of 3, that this is the geometric aspect of the derivative. If I know geometrically what a function looks like, well, then I can use the properties of geometry and of the slope and of the tangent line to figure out what the derivative looks like. For straight lines, it's pretty simple, because straight lines have a very well-defined slope. For a non-straight line, So suppose I have a line, a graph that's not a straight line. Something like that. So with this, it's a little bit tougher because it doesn't have a nice, well-defined slope. So what I'm going to do is find 3 slopes. And I don't have to be very exact. In fact, I'm not even going to put any numbers on this grid. All right, the numbers really don't matter. So this is the graph of F. So what I'm going to do is I'm going to find 3 slopes. And I'm going to put the word slope in air quotes. You know, I'm not actually going to use a formula. I'm just going to sort of wing it here. Let's find the easiest one, which is right here in the middle. The slope is 0. Yeah. So this is the point 0, 0. I said I wasn't going to put any numbers, but I am. What I meant by that is I'm not going to take a piece of graph paper and label every number. So the slope here at 0, so this is x, 0 for x is 0. So this becomes y. The slope of this graph becomes the y of the derivative graph. Now I got to do at least 3 different, I got to do 2 more places. So let's go right here. X equals 2. The slope is positive. So at x equals 2, I have to have some positive number. I don't know what it is. If I wanted to know exactly what this positive number was, then I would have to measure this exact slope, or at least approximate that slope. Over here, at -2, the slope is negative. Less than 0. So over here, at -2, I'm somewhere down here, some negative number. So generally, I know that my derivative looks like this. And again, I know the x values. The x values are very easy to find because they're going to be labeled. The y values are, they could be variable, right? It really depends on how steep this line is. So if the slope of this line was 5, well, then I would put this point at 5, If the slope of this line was -3, then I would put this one at -3, right? But it's really not going to change the answer. The answer is going to generally be a line that generally looks like that. Okay. I'm going to leave it as a DIY for you. So I can move on to the next example. If I flip the parabola upside down, then you would switch the positives and the negatives. And you would have something like that. Again, you should look at the graph that you're given and find 3 points and then estimate them over here. There is a tolerance, I'm not asking for an exact answer. I'm asking for, within the ballpark of possibilities of what the graph could possibly look like. I don't want to spend too much more time on this, but because we're going to have a whole section later in the chapter on graphing. But every one of these that I do now will just sort of plant the seed for the future. I want to show you the three most common. So I've shown you two very common ones, and then there's one more very common graph. Sort of this S-shaped cubic graph, it's called. So this is your F. Again, the X values kind of matter. So we'll call that 1, 2, 3. Three, and then 4. And then 1, -2, and then -3, and so on and so forth, -4, like that. Okay. So the X values are a little bit more important than the Y values in this because it's a function of X. Right. So for this one, I'm going to do 3 points again. Probably get away with 3's good. I don't want to say I could do less than that. So let's start at 0. X is equal to 0. The slope is positive. So over here, if X is equal to 0, just like the last example, I can't exactly say what the number is, but I know it's going to be some positive number. Now again, if I had a grid, if I had my graph grid, I could calculate that slope, and then I would have a better idea of what that number is. When we get to the graphing section, I'll consider actually having two grids so that I can swap them out. But this is going to have to do for this example. All right, let's do at least 2 more points. So let's do right here, X equals 2. Slope is 0. So at X equals 2, slope is 0. So remember, the slope here becomes the Y value here. And then over here, -2. Again, slope is equal to 0. So -2, slope is equal to 0. So the graph of F looks like this, or the graph of F prime. So this is the original F, that's the function, and this is the graph of its derivative. I think you might be seeing a distinct pattern, right? And that's kind of what I'm leaning towards in the end of this lecture here. So as I wrap up this lecture, I want to make it clear that we have now 3 definitions of a limit. They all produce the same result. So there's 3 different aspects or 3 different ways of achieving that. And then now we've thought about the results in 3 different ways: numerically, algebraically, and geometrically, or also known as graphically. So let's go ahead and just do some more examples. Example 10. Let's go back to the algebra. Let's do some functions that we have not yet seen. We have not seen any square root graphs yet, or square root functions. So find the derivative. F prime of X. Yep, all right, we got it. So lim H goes to 0. Square root X plus H minus 3 plus 9 minus the square root of x minus 3 plus 9 over h. Limit h goes to 0. I don't really need these parentheses. X plus h minus 3. Be careful here. This negative is going to change the 9 into a negative 9. So you're going to have a positive 9 and a negative 9, and those are going to cancel out. So this is all you're going to be left with. All over h. Now you can't plug in 0 for h until you first simplified this expression. So we've done this before. This is the special form of 1. We're going to multiply by a special form of 1. Special form of 1 is the same expression that you see in the numerator, but changing the middle sign. Now, I wouldn't do anything with the denominator. The denominator is just going to be this messy thing. I don't want to see you, I probably won't see you do it, but, I don't want to even imagine you trying to simplify the bottom. All right, don't waste your time. Put all your energy into simplifying the top. So you're going to get the square root times the square root. All right, those are going to cancel. You could put it in your notes, square root squared, and then cross them off, and those are going to be gone. Then you're going to have the square root times a positive, and then the square root times a negative, and those are also going to cancel. I'm not even going to write them. Those are going to cancel. I could write all that stuff right here. It would take 5 minutes, and then I just would cross them off anyway. All right, so I'm just going to put 2 big X's right here. Not the variable X, the canceling X. And then finally, I've got a negative times a positive, square root x minus 3 squared, and those are also going to cancel. And so I have f prime of x is the limit as h goes to 0 of x plus h minus 3 with no more square root. These are canceled. Minus x minus 3, no more square root here, all over this messy denominator. Which is the limit as h goes to 0, distribute here. X plus h minus 3 minus x plus 3 all over h, x plus h minus 3 plus x minus 3. Here's the canceling. I'll go ahead and cancel the h too now. I mean, I could wait, but I'm really running out of space. So I always tell you to wait till the end with the h, but I mean, this is the end. So now if everything cancels up top, just put a 1. It's not 0, it's 1. And then you have the square root of x plus h minus 3 plus the square root of x minus 3. Now this h is canceled, but the h inside the radical is going to go to 0. So that's going to give you the square root of x minus 3 plus square root of x minus 3. These are going to match now because the h has gone to 0. So these are twins. And what do you do with twins? You put a big giant 2 in front of the square root. It's not a little 2. It's not an index. It's a coefficient. It's 1/2. And that is your derivative. I'm not even going to try to graph this. It's not that hard. It's just not worth the time it would take to do it. If you're curious, it looks like a one-armed parabola. But it does have a hole, so it gets a little complicated. So for today's graphing, I'm done. I just wanted to show you lines and parabolas and that S-shaped, which is called a cubic. Those will be the most familiar graphs that you've seen. And we'll save this for a future graphing session when I've got more time. All right, there's really 2 of these kind of strange applications. I don't know if you call them applications, but strange exhibitions of the derivative. This is a radical or a square root function. Let's do a rational function. And then I'm going to do some business maybe at the end if I've got some time. I know I'm going on a little bit today, but it needs to be done. So let's do 3 over x plus 8. Find the derivative. So that's the limit. F prime of x is the limit. H goes to 0 of 3 over x plus h plus 8 minus 3 over x plus 8 all over h. This one's a little bit tricky because you might not think you need to do this. You might think you could like bring the x to the top and do some cleanup that way. I've tried it that way before. I had that same optimism at one point, and I just kind of gave in and said, well, this is the most effective way. Until we learn another technique, this is what we have. This is the tool we have. This is, of the 3 definitions, my favorite one. And it is the one that I will be using the most in this course. I do have the other 2 versions, and I'm not going to get rid of those, but they're just not going to come into play for the rest of today. So you remember how I like to write this? I like to use old school division. Old school 5th grade division. I also like to simplify this. 3 over x plus h minus 3 over x. Yeah, I'm trying to save a little space here, but you have a positive 8. And then you've got a negative 8. So those are going to cancel out. And then I like to use the old school division. Least common denominator. Right here, I want to multiply by x plus h, top and bottom. It's very similar to what we just did with the square root, but in this one, you have to do it twice. And then on this one, you want to multiply by x, top and bottom. And that makes the denominators the same. Don't try to simplify the denominator. All right, it's just like the last one. You want to leave the denominator messy. You want to do all your work in the numerator. And then you've got this old school divided by h. So you've got 3x minus 3x minus 3h. So when you distribute this negative, it changes the signs. Again, don't try to clean up the bottom. It's just x plus h times x. I've wrote one of them backwards here, but in the final step, I usually just write it this way, x plus h. Although it doesn't matter. I call this tomato. Makes no difference to me. And then remember old school, flip and multiply. You're flipping over the h, it becomes 1 over h, and then you change to multiplication. So I've got f prime of x is the limit as h goes to 0. Oh, look, 3x minus 3x. Those are going to cancel. H is going to cancel with h. Negative 3 is going to get multiplied by 1. That's negative 3 times 1. And then the bottom just stays messy. And that's going to be negative 3 over x squared. You see? Negative 3 times 1 becomes negative 3. H becomes 0. And so this is just x times x, which is x squared. You can write it like that, negative 3 over x squared, or you can write it negative and then 3 over x squared. It really doesn't matter. You could even be weird and write it as 3 over negative x squared. That's also correct. All three of these are correct. I usually just stick with the first one. Negative 3, because that's the way I look at it. Negative 3, and then over x squared. So when I'm doing a problem like this, I always know that I have 3 ways, but I just pick the one that is the most common. Okay. Well, I'm about ready to wrap this up. I've already gone over by a minute, but I do have time for one more example. Example 12. Maybe we'll save the business math for the next edition. Part 2 coming soon to YouTube. So we'll end with just another graphing problem. I won't draw the graph, but I'll just mention the graph. Find the slope. So I did some abstract graphing. This is a little bit more specific of the tangent line. It sort of wraps up the entire presentation today of the function f of x equals negative 2x squared plus 4x minus 5 at x equals 1. No, sorry, not 1. I changed my mind. Negative 1. All right. So find the slope of the tangent line at negative 1. You could do 1 if you want. I just want to do something we haven't done yet. So this would be very specific. In the previous graphing problems, I was just going, that slope looks like it's about this. I was being sort of wishy-washy about it. Now I want to be very specific. I want an exact number of what that slope is. All right. So let's first find the derivative. So let's go ahead and do that. The limit as h goes to 0 of negative 2x plus h squared plus 4x plus h minus 5 minus this really would be an in-class assignment at this point. I would probably write this on the board and then walk around and, before the class ends. But since we don't have that time together, this is our after assignment before you run out the door to get to your next class, because the bell's about to ring. We don't really have bells, but the silent bell of college. So I got negative 2x squared minus 4xh minus 2h squared plus 4x plus 4h minus 5 minus minus. This is going to be double negatives. That's plus 2x squared. Minus plus is minus 4x. Minus minus is plus 5 all over h. I'm in a little bit of a hurry now. Not too bad, but we've done a lot of these today. So this is more like I just kick back and see if you can follow all the steps. If I was doing a TikTok video, I'd probably have to go a lot faster than this, right? I'd have to be talking really, really fast. This is an H. That's an H. I killed the wrong one. So I kill the X's. See how fast I was going? I almost blew it. So that's not an X, that's an H. I do cancel the X's though. So one of the clues when you get to this step, every term should have an H. Oh, and I should probably do what I've been doing this whole lesson, and that's writing the H underneath all the terms. All right. And then I take the limit as H goes to 0, and I get negative 4x plus 4. Record time. That's our derivative in record time. Now you can kind of think about this back to the very first example. This is your A if you were using one of the other definitions. So again, I'll leave that to you. I have seen other professors and other students when I was in this this class, 30 years ago. Shit, it's probably been longer than that. 35 years ago. Where this number was plugged in earlier in the process and they're already done, right? Well, I'm still sitting there struggling. So again, I'll leave that as a freedom of choice. So what we really want is the slope of the tangent line. So f prime of x is negative 4x plus 4. So we just plug in negative 1. And instead of being, wishy-washy about, the slope is positive. Well, yeah, the slope is positive, but with the tool of the derivative, this very powerful tool, and with a specific x value, I don't even know what the y value is, and I don't care in this video. Maybe in the next one I will. In this lesson, I don't care. But I do know that the slope is 8. So that gives me a good idea of what the graph of the function looks like at this value. Well, I've already gone over time. Welcome to calculus. I've been saying that for a while, but it really began today. This is, now that we've taken the limit, which was really sort of the lobby, and we are now in the main building now. We have come into the real deal here. So the derivative is here to stay. I am Dr. Jordan. And until next time, I'll see you on the internet.